Hello everyone, I'm Ghasem Sharifi, and during this presentation I want to talk about my progress during the last year. My thesis is about mission operation of the ETPAC project, and my supervisor are Professor Gonzalo Sanchez and Andres Marcos. Just brief overview about the content. I'm talking about the motivation and thesis timeline, and after that I'm going to ETPAC mission and focus on operation of this, explain about ground station, mission control software, and some experimental setup and tests that we are performing. And also, lastly, I will talk about SLR sat Boiro that I was dedicated some time to working on ADCS subsystem on this satellite.
Get closer to the mic.
Okay. About ETPAC mission, you know that electrodynamic system is a promising solution for deorbiting a space application. And ETPAC mission is a project for developing deorbiting device aiming to launch at 2025. And basically it includes two modules that should be separated with a 500-meter long tether. And it's working by interaction of the magnetic field, the current along the tether, and velocity of the satellite to generate Lorentz force. And about the performance of this system, you can see for example, for a satellite in 600 kilometer altitude, if we don't have any tether, it takes more than 40 years to deorbit. And if we deploy tether, only because of the drag of aerodynamic, this time decreased to 3 months. And if we have a Lorentz force, we have ADT, the time decreasing to 70 days. And my focus on this project is about the ground segment and operation. That is the very key and critical activity that is started immediately after launch. And you can see here the structure and architecture of this ground segment. It includes ground station that is responsible to making communication link between the satellite and ground station. Now for that we want to use the Leaf Space company that they have distributed network and ground station different parts of the world. And for the secondary ground station, we are now establishing a ground station at UC3M University only for listening to satellite, only for receiving telemetry. Apart from that, we have a mission control station that is the main part of the ground segment, that there are lots of program, lots of activity that should managing the satellite from the ground station. And it includes the front-end and back-end software. And between these two, we have a network. We have a network cloud engine to interface between these two parts. About this timeline, first year I work in the ground station, and after that, during the last year, I work in the mission control station. And after that, we should checking the network between these two parts, to doing that the interface is working properly, and finally next year we will operate satellite in a real condition. About the mission control software, there are lots of tasks that we should, there are lots of concerns that we should cover. Just you can see all of the tasks that we should thinking about that already we programmed and developed lots of approach and a strategy for that. Just here I will talk about some of them. About post-processing data, we have the real-time and offline telemetry network. We have the mass properties identification is very important after launching the satellite. It's very essential to recalculate the inertia of the satellite. For the health monitoring, it's very important to monitoring and identify the faulty sensor and actuator during the mission, and taking action in order to fulfilling the mission. About the orbit prediction, it's very important to knowing the position of the satellite, because always we don't have access to the satellite. So we should predict the position of the satellite by using the GPS and also using the TLE data. Have an interlink between the BESMA, because you know that BESMA is a comprehensive software to simulate the tether mission. So we have an interlink between our mission, our software, and BESMA in order to predict the satellite. The mission task scheduling is another thing. Now we have a state flow chart to knowing that step by step after the launch what activities should be done for each phases, because basically we have 4 different phases, and for each phase there are lots of activity that should be sequential activity that should be performed. About the uplink command, now we have the list of the command. Now we are on the process of the testing, that being ensured that all of the command that we are sending to satellite is working properly or not. The magnetic calibration is another thing because our controller approach is based in magnetic actuation. So knowing and measuring the correct magnetic field is very important. So now we developed an algorithm for calibration of the magnetometer in flight. And finally, for the hollow cathode command, it's very important. You know, hollow cathode is a device to emitting electron, and because the hollow cathode is working in a specific current level, so we should have a strategy for triggering hollow command in only a specific time. And you can see the status of all of this activity. For some of them already we develop, we program and test, and some of them we are in progress, and some things that some of them is activity that in the future we should do. And from all of them, only we are talking about health monitoring and hollow cathode strategy. For the health monitoring, we have 2 modules, and for each of them there are 7 subsystems. And now we're covering for more than 20 sensors and actuators health monitoring system. And we define 3 different levels. The first is equipment level. So by defining some a range of operation, if our measurement going behind of this, we identified as a fault on the system. The another approach is another level is subsystem level. Sometimes only measuring the sensor output is not enough. So if the sensor has a redundant, we are comparing the output of the sensor with its redundant. And for some cases that there is not redundant, we are using another sensor in that subsystem in order to identify the fault. For example, for the gyro, we are comparing the data from the magnetometer, because from the magnetometer also we can get the angular velocity, so we can comparing these two output. Another level is satellite level. If we cannot identify in the subsystem level, we are using another sensor in different subsystem. For example, for the deployment mechanism, we are using the GPS data that is in the ADCL subsystem to knowing about exactly how much we deploy tether. And you can see here, this is only a graphical interface about the health monitoring system that we developed. Now we are under testing. About the hollow cathode command, as I mentioned, the hollow cathode is only working upper than 200 milliampere. And as you can see here, in each orbit, only fraction of time, the blue line, is a time that we should trigger the hollow cathode. And this is because of the avoiding the power consumption and wasting the explant. And for this, we propose 4 different strategies. 2 of them is based on knowing the position of 2 modules, because these 2 approaches is acting based on knowing plasma density, then emotional electric field, and we are using the GPS, magnetometer, and position of satellite. So these 2 approaches based on knowing the position of 2 satellites and accessing to ground station. 2 strategies we don't use ground station, is completely on the onboard computer of the satellite. One of them using the plasma density, and another using the sun angle of the satellite and its position. So this is the comparison between these 2 approaches. If we have enough access to ground station, the approach that use ground station have a more than 90% accuracy for triggering the hollow cathode. And if there is not, this approach is very general. They can apply for any type of tether mission. If there is not enough ground station access, the approach based on the plasma has a better performance. And you can see here the difference and the comparison between, if we don't use any strategy, this is the amount of wasting explant. And if we use this strategy, we can reduce between 5 or 10 times explant on the satellite. And finally, you can here see the graphical interface in the front end of the software. Now we have for the uplink command, for the camera, for the tracking, for the telemetry visualization, for the health monitoring, we consider and program to user-friendly. During the mission, we can see the status of the satellite. Also, we have some experimental setup in our university, so we can validate our program, our algorithm experimentally, specifically for attitude determination, for fault detection, for mass properties and calibration of the sensor. We have now experimental setup is basically working with air bearing, and it can provide for us 3 degrees of freedom. And the disturbance of the system is very low, so it's very useful for the experimental set of the CubeSat satellite. And you can see here the result of experimental set for attitude determination algorithm by using a reference sensor that is a PixHawk. It's very reliable sensor that using in many drones and quadcopters. So we are comparing our developed attitude determination algorithm with the attitude determination algorithm inside of the PixHawk to being sure that our algorithms working properly. And we saw that with after many dynamic tests, after some second, the error between our algorithm will be negligible. That means that our attitude determination working properly. Some of my program also was working on the stellar sat Boira in attitude determination ADCS control, and it's a 2U CubeSat aiming to measuring water vapor. And we passed 2 phases of PDR, and PDR now working on this critical design review. And you can see here some result of different mode of the satellite for the control. So finally, this is my publication. I have one journal about the Holocaust strategy in active astronautical, and I attend, and next we also attend to one conference related to ADCS control and experimental test that we perform. So finally, thank you so much for your attention.